Okay, here's problem 8 on page 553. I am excited to be part of this plan because this is week 13. Normally unlucky, but this is your lucky week because this is the last week of homework. This is homework 41. This problem 8 has a sister on the same, has two sisters on the same page, problems 9 and 16. And these three problems are about simple harmonic motion. Simple harmonic motion. And what they want you to do is they just want you to write down some appropriate equation. The problem says an object is attached to a coiled spring. It's pulled down a distance a from its rest position and then released, assuming that the motion is simple harmonic with period t. Write down an equation, and they give you a couple of parameters. So let's just do a little review. I've got a spring and a mass. There's a classic. I'm going to put it down here. Got a spring, I've got a mass. Classic picture. And this position, if this mass is just hung onto the spring and allowed to hang there and settles out into this position. This position is called the equilibrium or rest position. Equilibrium or rest position. And it's just the position where the force is balanced. There's a force down due to gravity. There's a force up due to the restoring force of the spring. And again, just left on its own, it'll settle there. What gets interesting is if you displace it from its position, because if you do, the restoring force of the spring, which goes like the elongation of the spring, goes directly as it pulls the mass back up versus gravity, and then it pushes it back down, blah, blah, blah. So you start to get this kind of motion where the spring goes up and down. So if I'm going to call this y of t, and I'm going to let that be the positive direction, I'm going to let this be the t-axis. So right here at the rest position, y is equal to 0. Then I'm going to describe this motion as y of t is equal to some amplitude. I pulled this down a distance a. It will, with no losses in the system, bounce up a distance a, and then it's going to oscillate sinusoidally with a amplitude of a. And in this case, I can choose sine, I can choose cosine, but the initial condition is such that at time t equals 0, I have pulled this down position A. So I've got to write it like that. So I could have just written it a cosine omega t, a sine omega t. I could do it a lot of things. But just to match this problem in which we have started things off by pulling things down, positive y-axis is this way, pull it down to negative a, if you will, then at time t equals 0, cosine omega t is 1, a of t is minus a, and I'm going to let it go. Okay, and so if I think about this in terms of the cosine function, it starts at time t equals 0 here, which is right here, which is right here. It's right there. It starts at negative a. It recovers back up to its rest position. It goes up as far as an amplitude of a, and then heads back down to its rest position, down to negative a, and so on and so forth. Okay, so this particular problem says this is problem 8, it says let a be equal to 4 and let t be equal to pi over 2, and let's remember that pi over 2, that t is 2 pi over omega. That means omega is, pi's go away, omega is going to be equal to 4. And if I would just stop talking, I could write down the answer to the problem, minus 4 cosine 4t. is the equation which describes this problem with this input. All right.